All right, so this is part 2 of looking at the metrics to measure how good the fit is. In the last video, part 1, we talked about correlation coefficient and residual plots. In this video, we're going to be looking at more metrics. So the first one is going to be standard deviation. So standard deviation in regression can be calculated using the G matrix. If you remember, after we calculate the G matrix, we also calculate S sub E, which is nothing but residual squared, and then we sum over all the data points divided by nu, which is the degrees of freedom. Okay, so nu by definition is going to be the number of data points minus the number of model parameters. Like if you want to do parabolic fit, so parabolic fit has 3 parameters, C1, C2, C3. And so in this case, nu is going to be the number of data points or number of samples minus 3. Okay, let's go back here. After we calculate nu and residual squared, we get this ratio. It's called S sub E squared. And then that goes into this equation to get the S matrix. The diagonal of the S matrix is going to be the variance of the parameters, and then the square root of the variance will be the standard deviation. So let's look at example. So we're going to look at example 7.3 and discuss each of these parameters. So here is example 7.3. I think we did that before, but we didn't actually cover all the metrics. Now we're going to look at those metrics in this video. Okay, so here's the same example. We did the correlation coefficient before. Now we're going to look at the S matrix. So S matrix, by definition, needs S sub E squared times the inverse of G. So we need to calculate S sub E squared first and then inverse of G. Okay, so here is S sub E squared, and by definition, that is going to be the sum of residual squared, which is the blue cell, divided by degrees of freedom. Okay, so degrees of freedom right here is, we have 9 data points minus model parameters. There are 3 model parameters, C1, C2, C3, right? We have 3 coefficients to find. So at the end of the day, your nu is going to be 9 minus 3 is 6, and that's why you have division by 6. Okay, so that's SE squared. Now we're going to go to inverse of G. If this is G, you can use the matrix package to calculate the inverse of G. Okay, and that's going to be this matrix, which I have here. Okay, I'm using M inverse, but make sure that you have the package installed, otherwise M inverse doesn't work. So this is the inverse of the G matrix. Then we multiply the inverse by SE squared, and we get this matrix. Okay, so that's exactly this times this for the first element. Okay, so this is the variance matrix. Then we get the square root of the diagonals. Like in this case, this cell would be the square root of the first diagonal, this is the square root of the second diagonal, and this is the square root of the third diagonal. Okay, so this would be the standard deviation. Again, G inverse, variance, standard deviation, which is the square root of the variance and the diagonal. Okay, so now we have the standard deviation. Then we go to basically measure the error bars. After we calculate the standard deviation, we're going to look at the error bars or the confidence on the parameter we calculated. Like, we're introducing these as the optimal solution for the best fit. The question is, my experimental points may have some variation. That means when I'm not really sure that what I measured in the lab is 100% accurate. Let's say if we have like 5% error in the experimental data, can we just transfer that 5% error onto the coefficients and say, with like 95%, I'm confident that my coefficient should be around this. So I'm going to basically sort of bring the error bars from the experimental points to the coefficients that I find from the fit. And that is called the confidence intervals, or the parameter confidence intervals. To calculate the parameter confidence intervals, we have to calculate the standard deviation, which we just did, right? That's these three. This is the standard deviation for C1, standard deviation for C2, standard deviation for C3, and that's going to be the square root of the variance. So S is the variance, square root of it is the standard deviation. We calculate S sub E. We need to calculate this t-distribution. And after we calculate that, we can go ahead and calculate the error bar, which is the lower bound and upper bound for every parameter Ci. So let's look at this t1 minus alpha over 2. So this is a t-distribution. Excel has a function that can calculate the t-distribution. For t-distribution, we need the confidence interval, which is called this alpha, as well as the degrees of freedom. So let's see how we can calculate the error bars or the lower and upper bound using the t-distribution for this example 7.3 in the textbook. So I'm going to move this one a little bit over here. You have to squeeze this a little bit and do that way. Okay. So let's first talk about the confidence interval. So confidence interval by definition is the parameter. I'm looking at the first coefficient. So the first coefficient was, if you remember, so this is the coefficient I found before, right? From the G matrix, if you remember, this is the C1, C2, C3. Okay, we're going to go back and exactly follow this equation. So this is going to be C1. Okay, so here's C1 minus t-distribution. So for t-distribution, the function in Excel is t inverse. If you want to find 5% error or 95% confidence, then we write 0.05, indicating 5%, and then comma degrees of freedom, we just said that's 6 degrees of freedom because 9 samples, 3 model parameters, so the difference is going to be the 6. So here's the t-distribution part, and then times the square root of the variance, and then times S sub E. So here's S sub E, which is the, I'm sorry, so this I21 is the standard deviation, which is square root of the SII. And then here is square root of K12, which is SE squared. Square root of that is going to be SE. So this is SE, and this is square root of SII. Okay, so this is the lower bound on the first parameter. We hit enter, and for upper bound, we get the same equation. Instead of minus, we're going to use plus here. So for lower bound, we had minus. For upper bound, we had plus. And we repeat that equation for, basically, you can just drag down. If you write it properly and freeze the SE, because SE doesn't change from parameter to parameter, then by dragging this guy down, I believe, yeah, so it looks like if you well, okay, you cannot really drag this guy down because my SII is in diagonal. And so by dragging this thing down, it wants to go down along this column too. So you better basically copy the equation to these cells and then just change the parameters, like for the second confidence interval, we have the second coefficient here, minus for the lower bound and plus for the upper bound, t inverse, so that's basically the same thing, square root of SE, which we froze the indices. And then this is the missing part. Now, with drag down, you cannot get this right. You have to basically type it because this thing is sitting diagonally. It's not like vertically. Okay, and so this is the square root of SII, which is the standard deviation. It's going to be the purple cell right here. So that's the lower bound. Upper bound, you do the plus. You do the same thing for the third coefficient. You get these confidence intervals. So statistically, that means if we allow 5% variation in the experimental points, then this would be the lower and upper bound for the coefficients. Coefficients should stay within this bound with 5% errors in the experimental points, or 95% we're confident that our data stay within this interval. Okay, so that was the confidence interval. Another thing we can talk about is the t-ratio. So what is the use of t-ratio? T-ratio is used if you really don't know which model parameter is necessary. Let's say for this case, I don't know if it's if the quadratic model fits better or the cubic model, right? So someone says, well, I'm gonna fit an equation like this. Yeah, this is a cubic equation, or it's third order polynomial. Another person says, instead of third order polynomial, I'm going to do only the second order polynomial from here to here. Okay, so the question is, which one really fits the best? The third order polynomial, the second order polynomial, or even the first? So that's where the t-ratio comes in. So I'm going to show you how we can basically decide which parameter is important, which parameter is not important. So we calculate the t-ratio, and t-ratio is calculated this way. You get the coefficient, the model parameter, divide by the SI, and this SI is basically the standard deviation. So we get a ratio ti, and then we go back to the t distribution table and measure or compare this ti with the ti from the t distribution. If this ti, the absolute value of this ti, if the absolute value of this ti we calculate from this ratio is less than 2, then we're going to drop that parameter. If this t ratio is bigger than 2, then we're going to keep it, which means it's significant. We have to have it. Let's look at this example, the same example we just looked at. So I'm going to go ahead and calculate the t ratio. So t ratio by definition is the coefficient itself. For the first one is going to be 12.185 divided by its standard deviation, which we calculate right here. So the coefficient divided by standard deviation gives me the first t ratio. The second one, the same way. So second coefficient divided by the standard deviation of the second parameter. And the third one is the coefficient divided by standard deviation of the third coefficient. It gives me this. Because all of them, the absolute value of all of them are bigger than 2, all of them are significant, that means the quadratic model is good. It has to be quadratic. The question is, what if I started with a cubic model? So let's look at example 7.4 from the textbook. This one deals with the cubic model. So in other words, let's say someone didn't know that cubic is the best and started with, didn't know that quadratic is the best and started with cubic model. Okay? So here's example 7.4. We start with cubic model, and we're going to test which one of these are necessary, or which one of these is necessary, and which one is not necessary. So then we're gonna drop the ones that are not necessary. And this way, basically, we can just keep those ones that are significant. Well, keep those terms that are significant. Okay? So stay tuned for the next video on how we can basically make the model better by dropping unnecessary terms.